Hello and welcome to my presentation today. This is a presentation on what I will soon be using for my 8th grade recital project, which is an idea for a carbon mineralization device. So first I'll go through the problem which I'm trying to address, which is global warming, and some of its effects. Then I'll go through some solutions that already exist and how they're working out. Then I'll go through the solution that I'm trying to work on and other solutions that are alike to it. Now, here you see in the background the White Cliffs of Dover, which are, by weight, nearly half carbon dioxide, and they are an example of natural carbon mineralization. First, let's start with the problem that I'm trying to fix, global warming. Now, as most everyone knows, global warming is caused by the buildup of gases that trap reflected sunlight. Now, the gas that contributes most to this is carbon dioxide, as you also probably know, followed in far second by methane. Now, carbon dioxide is naturally created by animals, fungi, and EU bacteria, and absorbed by plants and protists. Archaebacteria, which are the last of the 6 kingdoms of life, live in environments free of oxygen, usually at the bottom of 2,000-degree lava wells, and so they don't contribute to the carbon cycle. Fossil fuels. Usually this cycle is able to self-regulate and stay at around 280 parts per million of carbon dioxide, shifting in natural cycles, giving you ice ages and other climate events. But this happens over long periods of time, such as tens of thousands of years, which gives lifetime to adjust to the new climate. Since 1850, however, humans have begun burning various forms of biomass, such as wood, coal, natural gas, and fossil fuels in general, in significant amounts. This has caused the carbon cycle to go off balance, and the carbon levels are rising too quickly for the plants, which we're also cutting down and burning, can't keep up. And now carbon dioxide levels have reached 400 parts per million, and they're still rising. Even in cases such as this, where the climate goes way off balance, there's usually processes that slowly absorb carbon dioxide from the atmosphere in other forms. Unfortunately, these processes require thousands of years, during which a large percent of life will die or be drastically altered. For example, here we see a graph of the rate of extinction, which shows that recently the number of extinct animals have been going up and up and up each year. Now, part of this is due to overhunting, overfishing, and over everything, but part of it is also due to global warming killing off these animals, or at least making them weaker. Now let's go into some of those effects of global warming. Now, the high level of carbon dioxide does damage both directly and through creating global warming. Global warming causes increased risk of natural disaster and extreme weather, and these climate changes can force species to move into new habitats. It can destroy their habitats, and this often interrupts the food chains, or food webs as they should actually be called, and leads to destruction of the chains, which kills many of the species around it. Lastly, combined with logging, it causes desertification, which makes areas almost uninhabitable for almost all forms of life. This background right here is of recently desertified land. Now, the one direct effect that I was talking about is ocean acidification. The lakes and oceans of the world take in around 35% of the carbon dioxide that we produce, which is roughly equivalent to 22 million imperial, or 2,000 pound, tons. This carbon dioxide is captured as carbonic acid, and this effect is referred to as ocean acidification. Here we see a diagram showing what the effects are. You'll see in a second that it destroys shell and coral life by changing the structure of their shells from carbonate to bicarbonate, which can dissolve in the water. Now, it affects coral and shell life, although coral is the most apparent at the moment since it's a very delicate species. You've probably heard recently that a lot of the coral reefs are dying for 2 main reasons. 1, that their shells are being disintegrated, and 2, coral bleaching, which you may also have heard of, which is a non-direct side effect of carbon dioxide. It's caused by global warming, and that's when the waters get too warm, they eject the symbiotic algae that lives with them. So it also affects fish and other marine life, and no doubt as the levels continue to rise, we'll discover that it affects more and more creatures in ways that we hadn't expected. For example, there's also preliminary findings that indicate that fish are being affected. Certain neurotransmitters, which are crucial to the functions of the nervous system and themselves in general, are being misformed, leading to confusion, sensory loss, and eventually death. Now, how will this affect humans rather than Nemo? We humans are not unaffected by these changes, although we overwhelmingly believe that they won't impact us. We will suffer the consequences. Now, in the Yale Project on Climate Change, they did a survey which showed that only 32% of people believe that climate change would affect them directly. This was done in the United States, and so people think here that they are going to be more sheltered from the effects. And as people get farther and farther away from them socially, they expect that they will be affected more and more. But this isn't true. Extreme weather will occur on a global scale. We can't stop that. The environment will no longer be able to filter harmful chemicals such as sulfur oxides and nitrogen oxides. Areas that currently have good climates for agriculture, such as the Central Valley near me, will migrate. Water levels will rise, sinking some islands entirely and flooding coastal areas. In addition to the ocean levels rising, some of the cities will start sinking. The eastern United States is a great example of this. Now, thousands or millions of years ago, when the ice caps were first formed, they put a lot of pressure on the land, and this caused the other parts of the tectonic plate to rise as a result. And now that the ice caps are melting away and those miles of ice are no longer putting pressure on it, the tectonic plates sink back down, like it's happening to the eastern United States, which makes the problem twice as bad. New Orleans, you can see right here, has recently been dipping below sea level, and since they are next to a lake rather than an ocean, they are seeing the consequences of this with easy flooding, with more often flooding. There are many other places around the world where this is also happening. Now, uncoincidentally, the coastal areas and places that we have favorable climates are where we place our major centers of population. That's why San Francisco and the Bay Area is such a large population center, which means that these factors changing will affect the largest portion of population and productivity. Now, there's also the fact that we continued on the existence of plant and animals for food and water, and also to filter those harmful chemicals like I mentioned earlier. Estimates claim that with the best technology it had, it would cost $46 trillion to replicate the immediately obvious services that the environment provides to us, compared to the $71.83 trillion gross world product, over half of it. Here you see a picture of the U.S. debt ceiling, which is $16.394 trillion. We would need 3 times the amount of money displayed in this picture to replicate the effects of the environment. And each of these little blocks in the picture is $1 million. Now, the amount of natural resources that we're using constantly rises as our population grows and as our standard of living increases as we start to use more stuff per person. In short, humans will definitely feel the effects of climate change, and we already are. Here's a picture of Paradise Glacier falling into the ocean. Now, why carbon capture, carbon mineralization? There are 3 main ways to prevent climate change, which fall into 3 main categories. Carbon emission control, which is limiting the production of carbon dioxide in the first place to stop it from existing. Geoengineering is the idea of changing the entire planet to take in less heat or to be able to absorb the carbon dioxide. Usually this is done by increasing albedo, or the amount that the Earth reflects, rather than actually dealing with the carbon dioxide. And carbon capture, which is directly removing carbon dioxide from the atmosphere or from power plants and storing it in a stable form. Now, this is also sometimes considered to be a subcategory of geoengineering, or when the carbon dioxide is taken directly from power plants, carbon emission control. Now, carbon emission control. This is the most popularized way to stop climate change: reduce, reuse, recycle, although that refers to plastic often, that impacts the amount of carbon dioxide we produce. Sadly, this will probably not be enough to stop climate change. Many studies are now showing that unless we completely stop emissions in the next decade, 5 years, 2 years, depending on who you listen to, which is completely impractical considering the astronomical investments we have in hydrocarbons as a fuel. Although we can do some things to lower our carbon impact, we can't completely eliminate them in this time. And it'll be too late to avoid many lines, red limits, disasters, or tipping points. And we're already seeing many effects of climate change. Machu Picchu will never see snow again, likely, and in 15 years the North Pole will no longer have solid ground. Although the rate at which carbon dioxide emissions are increasing has decreased, emissions overall are still increasing. In addition, we think that the ocean may be reaching maximum capacity for absorption of carbon dioxide, and may actually start to release it in the future, and planets strangely become less efficient at higher carbon dioxide concentrations, and the albedo of Earth is decreasing due to melting ice, which means that it's a vicious cycle and will continue to get worse and worse as time goes on. And the UN just released a new statement at the end of 2013, which said that they thought that the new worst-case scenario was 7.3 degrees Celsius by the end of the century, which is 4 degrees up from their estimate only 10 years ago. Now, geoengineering is the second way. Now, geoengineering, as I mentioned before, is the idea of modifying the entire Earth to simulate environmental changes that cause cooling. Usually, this is through increasing albedo, and the most commonly talked about method simulates a volcanic eruption by releasing lots of sulfate aerosols into the air. Now, this is done naturally by jet airplanes already. They emit it as pollution, although, understandably, it is pollution, and a lot of people want to get rid of it. However, geoengineering people think that we should increase the amount of aerosol pollution that planes put out, not try to decrease it, and they're going to try and put special chemicals in the plane's fuel supplies, which will do this. Now, while it's harmful to all animals, especially so this applies to birds, since they have very sensitive respiratory systems, and since it's up in the air. Although, eventually, they think it will land in anywhere from 6 months to 5 years, at which point it'll do damage on the ground too. Now, there's another popular method of geoengineering, which is dumping iron dust into the ocean to create algae blooms. You can also dump iron compounds which algae can absorb, such as iron sulfate, as was done in the study here shown. It was very controversial, but a company near me, actually in San Francisco, decided that they were going to release a ton of these iron sulfates into the Pacific Ocean as part of a test. They think it may have worked, however, it can cause great damage too. While this actually takes in the carbon dioxide and deals with the problems that ocean life's experiencing from the high concentrations of carbon dioxide rather than just dealing with the symptoms of the temperature, it also blocks light from getting down deep into the ocean, and thus kills off much more life than it could hurt down there, than it could help down there. However, also geoengineering is still quite theoretical, and it has yet to be implemented on a full scale, and there's a lot of opposition to it, so it probably won't be. Now, carbon sequestration. As I mentioned, it's sometimes considered to be a subcategory of geoengineering or even carbon capture, but I think that it's its own method all alone. Now, usually this is considered to be the process of directly removing carbon dioxide from either the atmosphere or from an enhanced source, like car exhaust or flue gas from a power station is the most common one right now. Now, the current method of carbon sequestration that's most widely used by tons of countries around the world is collecting the CO2 from power plants and pressuring it into liquid CO2, which, yes, can be created if you pressurize it to 5 atmospheres or above, and you pump this down into expended oil wells, or methane and brine wells. And this brings up more fossil fuels, which we then end up burning. Now, the problem with this method is that we don't know if the carbon dioxide will be re-released into the atmosphere later. There's also another method, which is dumping it really far down into the ocean, so it forms a lake of carbon dioxide down there. Of course, this makes it so that there's hardly any oxygen that can reach down there, and it also creates a huge puddle of unlivableness at the bottom of the ocean, which could kill many animals down there. Now, while this appears to be very eco-friendly to the oil companies, it actually creates a net increase in carbon dioxide, and if the carbon dioxide is re-emitted afterwards, it would be much worse. Now, there's another method of carbon capture. There's a fine difference between carbon sequestration, which is the method I just described, and carbon capture. Now, carbon capture is the conversion of carbon dioxide into stable forms in which it can be stored, such as lime or calcium carbonate. This process occurs due to aquatic organisms that produce those shells, such as corals and mussels, and their shells slowly break down over time, and if they aren't acidified by the ocean, they form calcium carbonate, which is then taken into the, or sodium carbonate, on the other hand, which is what we saw in the diagram before, which is combined with silt and clay to form chalk, which is what the White Cliffs of Dover are made of. And that's why I have them as the intro picture. Now, this process of carbon capture, sadly, takes thousands, if not hundreds of thousands of years to stabilize the climate, and so it isn't very useful normally. However, there is another method for carbon capture, which is to synthetically induce it. What you do is electrolysis of brine, which is also known as the chloralkali process, which yields sodium hydroxide, chlorine, and hydrogen gas. And the sodium hydroxide produced is then used to capture carbon dioxide either from the air, which has 0.04% carbon dioxide, or from car exhausts or flue gas from a power station. And this permanently traps it in a solid form while producing hydrogen and chlorine. The chlorine is a useful product and can actually be sold when combined with metals or the hydrogen produced and yield back a lot of the energy. Now, here's a diagram of one of my earlier versions of the carbon capture device that I'm building. You can see here, it may not be the best handwriting, so you may not be able to read it, but here's the electrolysis cell, and there's a membrane separating it, stopping from bleach from being formed, which I'll go in more later. It's slowly taken from the bottom where the heaviest sodium hydroxide accumulates, which then, being bubbled, turns into sodium carbonate, which is even heavier, pulled into the next chamber, evaporated, giving you pure water, which also arises from the hydrogen being burned from the air. It gives you the solid carbon dioxide storage, and it gives you some hydrochloric acid, which, while normally branded as something very dangerous, toxic, and evil, is actually very useful, and can also help to reduce carbon emissions, since it usually costs a lot of carbon dioxide to be able to manufacture it. Now I will go over the basic principles under which the CCD operates. Now, the CCD process, as I mentioned earlier, also known as the chloralkali process, is going to be run by solar panels, and it'll convert brine solution of sodium chloride, salt, and water into sodium hydroxide through this reaction, and eventually into carbonate through this reaction. The sodium isn't shown here since it's just overall hydroxide that I'm using for the demonstration. And that can also be replaced in calcium, which it will be in later versions. Solar electrolysis of brine into aqueous sodium hydroxide. Now, this next bit's very technical, so if you want, you are absolutely welcome to skip it. With a fairly cheap ion exchange membrane and carbon electrodes found in car batteries, the ion exchange membrane is called naphion, and you can see some of it here. The electrolysis of brine produces hydrogen gas, sodium hydroxide, and chlorine gas. This, as I mentioned plenty of times before, is also known as the chloralkali process, and it's a multi-billion-dollar industry. It also uses 2% of the United States' electricity. It's a very energy-consuming process, so recapturing the energy afterwards is a very important thing to do. The hydrogen gas is reacted with air to feed that power back into the plant so that you can decrease the energy cost. And this produces pure water as a byproduct, where you feed in brine water, and eventually you could even feed in ocean water if you had a thick enough membrane. You also produce chlorine gas, and while not immediately useful, and it may seem like a hindering effort, it actually can become useful if you combine it with metals to produce metallic chlorides, which are actually quite valuable, especially aluminum chloride and magnesium chloride. Now, capture and storage. First, you have to, you may need to purify the air, because normal air, while 400 parts per million is a lot in terms of the 280 parts per million it is normally, this still means that it's only 0.04% carbon dioxide. So if you use air from a car exhaust, that ends up being around 20% carbon dioxide, which is a great increase, which makes it able to absorb the carbon dioxide much faster. Once this is done, once you purify the air, or if you take it from a good source like a car exhaust, you'll feed it in through the system with an expensive aquarium pump and a frit or air stone that disperses the bubbles so that there's more surface area for the carbon dioxide to be absorbed into the water. Then you just evaporate the resulting product to get out the sodium carbonate in powdered form, and it's then stored in a solid state. So here was the original idea I had. So this would be a household scale device that people could purchase to have in their individual households. You would have, the entire thing would be self-contained. You just need to put in more brine solution, and you need to take out the hydrogen, chlorine, whatever byproducts end up being there in the end. The hydrogen, would be burned, but the chlorine may end up in the end, or it could be a metallic chloride, or one of the solutions I had was to combine it with the hydrogen and form hydrochloric acid, but I later discarded this idea. I'm now looking back into it, which I'll explain in a minute. And now let's go on. So there would be the stages of design. It would be a modular system, so that you'd be able to buy. First of all, would be the seed, which would be what I do for a prototype. And this would just be a cell that bubbled air through. It wouldn't be an electrochemical cell. You just buy the sodium hydroxide, put it into the cell, and it would convert it into carbonate. Now, I did the calculations, and based on the cheapest prices I could find online readily, it would cost about $1,000 to offset a single average male human breathing per year. And then you could include the cell for sodium hydroxide production, sprout. And this stage would include 2 small carbon electrodes, which are quite cheap but very effective. They don't corrode for a long time. And it would have 2 grating plates and 2 wedges holding the Nafion membrane in place. We made a kind of prototype of this here. And you can see we have 2 plates, or maybe you can't see, that would hold it in place. Now this would be plugged into the stem unit, which I'll get to in a minute, or just a wall outlet, and it would end up offsetting around 200 times more carbon dioxide than is produced by the electricity generated, so it isn't a concern that you're using it from any sort of coal power station. Now, this model, obviously you wouldn't be able to buy the sprout, because it would just be an intermediary model, because it would release the hydrogen and chlorine into the atmosphere, or your living room, in the case when I was making my prototypes, which probably isn't very good for your health. And so, you would want chambers for collections of the byproduct, which I named sapling. The stage would have a 2-part lid for collection of the hydrogen and chlorine, and a filter going down the middle, extending off of the Nafion membrane, that would stop the hydrogen and chlorine from mixing. You also want to prevent any hydroxide from getting over the gap, which is what the Nafion's for in the first place. It stops chlorine and hydroxide from coming into contact, which forms bleach instead of sodium hydroxide. Now, this would flow into a couple of gas cylinders, or in the prototype I made, just into a 3D printed container. And finally, the final version of it, which would be purchasable and which would be mostly self-contained, you'd need to add in more brine, as I mentioned earlier. But besides that, it's pretty much self-contained. It would add a neutralization chamber, an energy feedback system for the hydrogen, and an evaporation disc. Although the evaporation isn't necessary, the sodium carbonate solution is fine on its own. In this stage, the chlorine would be drained into an acrylic double-layered vacuum-encased reaction chamber. Was my original idea, where plant matter, just from your yard or from scraps that you have around, would be put into the device through a triple-sealed sliding vacuum pumped tray system to ensure that there was absolutely no contamination of chlorine. This would slowly accumulate as inactive bleached pigments, as happens when chlorine comes in contact with organic matter, and also decompose cellulose at the bottom of the container. The hydrogen is then mixed at a control rate with normal air, reacted to give water and heat, as mentioned before, and the aqueous sodium carbonate is slowly drained out from the bottom, since it would accumulate there, being the heaviest, at 84 grams per mole. Now, power. The power would be provided by solar panels, as I mentioned. Alternatively, it could be plugged into the wall, although solar is a much nicer solution. So there would be branches, which would be 2 mesh layers of sculptor's copper, which you can see here, between which you would sandwich solar panels, 3x6 solar panels, which you can buy from many corporations, Everbright Solar, ML Solar. They could be provided as a standard, and they have small tabs on the side which you simply tie into it, and they automatically connect in parallel. The tabs are for connecting in series, which allows you to increase the voltage, and in parallel to increase the amps. You would increase it in parallel, and then connect 5 of those in a row, since solar panels as a standard produce 0.5 volts, and this would plug into something like a gold zero energy converter, which would bring it to the optimum voltage for the electrolysis to take place. Now, there are some problems with this version. The chlorine disposal system was impractical, as you heard from those triple-sealed, double-sealed vacuum glass encasings, and considering the amount of regulations around chlorine, it would end up costing millions of dollars to get it tested and improved for a household situation. Plus, not too many people are okay with the idea of having chlorine and hydrogen explosive gases in their house. Cost: the device would end up costing around $300 roughly, and this isn't including the solar panels, which you would need for any good amount of function. You would need quite a few solar panels, which is much too expensive for the average family in America. And effectiveness: considering the scale, there would be when I meant no option for energy capture, what I meant is like heat recapture from the carbonates. Some of the reactions in there actually do produce heat. The hydrogen could be done quite easily, but there are other options to improve efficiency on larger designs that simply wouldn't be an option on these smaller scales without drastically increasing the cost from where it is already. And this makes the device efficiency similar to a tub of algae by area. It would be between 60 and 240% efficient, although, as I mentioned, it would be on the lower end of that spectrum, since you can't get very efficient with such a small-scale device. Now, the new plan, CCD Mark II, with a much nicer picture. The following is the new plan that I made, and this would be a single large device, or multiple large devices, but initially it would just be a single device, which would be upgraded over time, rather than being a modular, instantly ready product. And you would slowly increase the number of solar panels, the area, the brine capacity, and just upgrade the components as you had funding over time. Now I'll go through another quite technical description of it that shows the four main components: the electrolysis core, the energy recovery system, the carbon saturation system, and the chlorine storage and disposal system. So first we'll start with the electrolysis core. The electrolysis core would be the main component of it. This is where the electrolysis obviously happens. All of the products would flow in and out of here, and this would be where the electrodes, the brine, everything would be contained essentially. It's the brain of the device, as close to a brain as you can get with an electrolysis cell. It'll be equipped with two titanium, gold, or carbon electrodes. I'll mention the benefits and problems with each later, or possibly gas diffusion electrodes, depending on how much funding is available. And now let's begin. So the membrane, which I mentioned extensively earlier, this Nafion membrane right here, would be used to separate the two halves of the cell. This membrane can be anywhere from 0.005 inches thick to 0.001 inches thick. The model I have showing you right here is 0.005 inches thick, or about 1/10 of a millimeter, although it's quite strong, seeing as it's made of a Teflon, essentially, with some sulfonic acid groups, which allow the ions to pass through selectively. As you may have seen in the animation at the beginning, sodium is allowed to pass through, chlorine and hydroxide are kept separate. This is used in the chloralkali industry to prevent the formation of hypochlorides like bleach that I mentioned earlier from forming and disrupting the formation of sufficient sodium hydroxide. Thicker membranes, such as this one, this is on the thicker side, 1/10 of a millimeter, are able to handle pressure differentials of 50 psi, which might arise when the hydrogen and chlorine build up in large enough amounts. But there's also more efficient Nafion 212 and 211, which are much thinner. Although just by increasing the area, you can increase the amount of this is usually the limiting factor in terms of speed of the reaction, since it's very slow for stuff to move across the membrane. Considering that it's tens of thousands of atoms thick, even though it's very thin in our scales. Now, for the larger scale, we may want to use slightly thicker membrane. You can purchase that, although again it's even slower, but you can just increase the surface area to make up for that. The material is relatively expensive, although considering that it's a one-time investment, it isn't that bad. It's approximately $1,000 per square meter, which means that a small amount like this costs around $25. Now, the brine solution. Optimal brine solution concentration would be between 25 and 33% weight for weight concentration, which is about 33% molar concentration, since salt's a lot heavier than water. And as you can see back in this diagram here, if you read carefully, there's 26% salt going in and 24% salt coming out. A lot of plants operate at 25%, but 33% is the theoretical maximum amount of salt that you can pack in. Now, you want the brine solution to be quite pure, otherwise it can damage the membrane. Although, with thicker membranes, that's not really a concern. It takes years and years for them to wear down. Now, the electrodes that I mentioned earlier, they would either be carbon electrodes, gold-plated electrodes, titanium electrodes, or gas diffusion electrodes. Now, the graphite rods are extremely cheap. You can get them out of car batteries or just normal carbon zinc batteries, which usually aren't that common anymore. They are low reactivity, they are very high surface area, and however, they're not that conductive. About 3 orders of magnitude less conductive than all the other ones mentioned here. Gold-plated electrodes, not entirely gold electrodes, are relatively expensive. They are low surface area, extremely low reactivity, and they are very conductive. However, titanium, while it's only moderately conductive, relatively low reactivity, and specifically it doesn't react with chlorine, which is important, it has a low surface area and high cost, which makes it seem like it's not going to be so good. However, titanium acts as a good catalyst for the reaction, which lowers the amount of energy needed. So ideally, you would actually use the titanium electrodes, and these are what are commercially used in chloralkali plants. You can see a picture of one here. You can see these are much more, these are actually industrial scale models versus the other ones. Carbon electrodes are also used in industrial scales, but less often in the chloralkali process. There's one other possibility, which is gas diffusion electrodes, which have recently been developed. Now, gas diffusion electrodes, they're something that goes on top of the electrode, so you could still have a titanium gas diffusion electrode, which gets you the good advantage of the catalyst. But what gas diffusion electrodes do is they release oxygen into the water. And so instead of producing a hydroxide and a hydrogen, you get 2 hydroxides, which doubles your productivity of hydroxide. This means that you can double your productivity of, obviously you're not decreasing the energy by increasing how much you're producing, but you're able to double the rate at which you can produce the hydroxide on the other side, since the charge difference doesn't accumulate. Of course, this is assuming that you don't have the membrane as the limiting factor. Now, pressure and flow regulators. On any large scale, the device would have pressure and flow regulators to measure the brine levels and to take them out at very specific concentrations, measure the hydrogen chlorine gas, make sure that you aren't about to have an explosion of those, and it would test for the presence of hydroxide against carbonate so that you know when you want to remove it. And now the energy recovery system. This is very important since it allows you to greatly decrease the amount of energy used if done properly. Now, there are lots of inefficiencies in the system. There's resistance from the brine solution, which is a very great concern. There's maybe a total drop in the Gibbs free energy that's actually produced when you complete the end-stage reactions. There are certainly some reactions which are exothermic in the process and which you can capture energy from. The main inefficiency at the moment is the electrolysis of water. As I mentioned before, without the gas diffusion electrodes, it produces excess hydrogen, which is a big waste of energy. The chlorine is the second largest waste of energy, since that has an electron affinity of 351 kilojoules per mole, which ends up translating into a lot of electricity. Now, the gas diffusion electrodes. As I mentioned earlier, they add new oxygen to it, and this removes one of the inefficiencies, and it means that more sodium hydroxide can be produced in the long run. Not in the long run, more can be produced. Without the GDE electrodes, gas diffusion electrodes, the excess hydrogen has to be burned, and the excess heat has to be captured from that. There are many ways to do this, from plate heat exchangers, thermocouples, and oil vapor systems. I won't go into those. But it also depends what you burn the hydrogen with. Now, I mentioned earlier that you would usually burn it with just oxygen present in the air to produce water and a fair amount of heat, although you could also react it with the chlorine that you produce, and this produces a lot more heat. And now the carbon saturation system. This could be considered a subsystem of the electrolysis core, but since it also plays into the chlorine storage and disposal, I figured that I'd leave it separate. And now onto that. So the source of carbon dioxide. As I mentioned earlier, you may want to purify the air, or you may want to use a car exhaust or flue gas from a power station as your source. You need an air pump. This isn't costly. They're very common, and they're easy to get. This would just needs to split the air into very small bubbles so that you can aerate the entire water and have a much higher surface area of carbon dioxide, which can be absorbed, trying to convert into carbonic acid and then eventually into sodium carbonate. And chlorine storage and disposal. So the first step of that is the containers. Now, if there isn't an ample supply of metal so that you can continuously react it, you'll have to have containers to store the chlorine, or you could actually just ship off the chlorine as its own product. Now, most containers aren't suited to carrying chlorine, so these can be quite expensive. However, if correctly dehumidified, the chlorine can be stored in relatively inexpensive aluminum cans. Aluminum, not cans, tanks. So often it's a common practice to remove humidity from the chlorine. Now, this can be quite an energy-expensive process, and you don't get to any of the energy back since you're not reacting the chlorine if you're just storing it in tanks and exporting it that way. So usually this isn't favorable. However, it does make the tanks a lot cheaper. Although you have to remember that the tanks are a one-time investment, so you have to see how long you think it will be operating for before you go into that. Now, removing dissolved chlorine. This step will almost certainly, you don't need an additional system for this. As I mentioned earlier, the carbon saturation system plays into this, because by bubbling all that air through, you get rid of any dissolved chlorine in the water, which could be a problem. And finally, a reaction chamber for the chlorine. So if you're not going to export chlorine, if you're going to react it with something, which gives a lot of energy back, some of the reactions it carries out with magnesium, iron, aluminum, or hydrogen reach up to 2,000 degrees Celsius. So you're going to need something that's able to hold that kind of temperature, acidic conditions, high pressure, and be capable of holding gas, liquid, and solids without any chance of leaking. Luckily, and surprisingly, there are a number of materials that fit this list, including glass, a rather obvious choice, so this isn't actually that much of an area of concern. Now, the metals. As I mentioned earlier, it can be reacted with hydrogen, or magnesium, iron, or aluminum. Now, magnesium chloride is safer than the other two options, and it doesn't have to be dehydrated for sale. Magnesium hexachloride is usually sold. That's what it's sold as, usually. Which means that it takes less energy to dehumidify it, or just remove the water from it. It outputs more energy because magnesium is more reactive. However, it's much more expensive than the other options. Iron is the cheapest metal, usually only 35 cents per pound. However, it's a bit more dangerous than aluminum chloride, a lot more dangerous than magnesium chloride. Although we're talking in quite small scales here, it's only a 3 on the fire hazard health risk, fire diamond health risk, whereas magnesium hexachloride is a 2. It is slightly reactive, so you have to be careful about how you store it, and it isn't particularly valuable, so this isn't probably the best path. However, aluminum, it's only slightly more expensive than iron, weighing in at about 50 cents per pound. It's slightly more dangerous than magnesium chloride. It's also a bit safer than ferric chloride, and appears to be much more valuable, selling it up to $2 per ounce. Now, there's similar ideas I discovered. Once I had come up with this idea and I put it down on paper, I started to research things for it, and I stumbled across Calera. So Calera is an industrial-sized plant that's a for-profit company that produces calcium carbonate as their final project. So their aim is to use calcium carbonate to produce concrete, and concrete makes up 5% of carbon emissions worldwide right now, which means that they're actually offsetting, besides the fact that they're producing it from carbon dioxide in the atmosphere, so they're trapping carbon dioxide, but they're also in a much greater act of carbon saving. They are stopping the need for lime mining, which contributes a lot more to carbon dioxide. In fact, about 5 times more is saved that way. At the moment, they use flue gas from the power station, and they import the calcium hydroxide that they use, also using some magnesium compounds to make the reaction faster and give off more energy. However, they are developing a system for producing sodium hydroxide, which uses 1/5 of the energy of the normal chloralkali process, which they call the Abel process. This is heavily patented, and so it'll be a long time before anyone else will be able to use the methods, but it's quite interesting to look at. Now, the founder of Calera works at the University of Berkeley, which is quite nearby me, and I hope to contact him soon. And hopefully he could be my mentor for the 8th grade recital project, which is what I'll be doing this for. Now, there's another corporation which I just discovered a few days ago called Skyonic. Now, Skyonic has just begun construction of their first plant. They're based in Austin, Texas. They're quite similar to Calera. However, they start further back in the process. Also, they produce sodium hydroxide by electrolysis, just like I hope to do. And this makes their research more valuable to me because I can see how they deal with issues like the chlorine disposal. For example, I had discarded the idea of combining the hydrogen and chlorine since hydrochloric acid is a gas under those conditions and has to be boiled through water, and while it's a gas, it's much more dangerous. However, it looks like it does have some very good advantages, so I'm going to do more research into actually using that idea rather than the metal chlorides. Now, how is the carbon capture device different from Skyonic then? So both of these companies are for-profit organizations, and they've both admitted that it's very hard to keep their companies running, and it's likely that they may shut down in the next few years. This means that any money they produce is taken out of the system rather than reinvested, and there's no involvement from the public. They're very closed off. And there's only so large a market to which they can expand. It's estimated that there can only be 250 plants to which they would satisfy the entire world's sodium bicarbonate baking soda needs, and it would no longer be a viable industry for them. However, the carbon capture device will be non-profit. You'll donate money, and the money will be reinvested back into the system from any products that are sold, which means that it can grow, theoretically, exponentially, although practically there'll be upgrades that need to happen over time and repairs, so that it'll be a less steep growth. However, it will still be faster and faster growth that will happen, and since there's no need for continued income after a while, if you're willing to stop growing, your product can continue functioning outside of the market. It doesn't need to sell products to be functional. So, my long-term plan. Eventually, I hope to make a Kickstarter campaign to fundraise for the construction of the initial device. And after the device is constructed and all the plans are approved, and it's built in place where you can fairly infinitely expand land onto further space outwards, since you'll need a lot of land to place solar panels on. A website will be created through which people can calculate their carbon footprint and offset it by donating money to the project. Now, unlike most carbon capture systems, not carbon capture specifically, but carbon offsetting systems, this will work continuously. So a one-time donation will continue to count against your carbon footprint, and it'll continue to sequester carbon all the time based off that one initial investment. And as I mentioned before, further donation helps in that as you expand, it's exponential growth from the products being sold and reinvesting the money back into it. Now, once people have contributed, or even if they haven't, they'll be able to view statistics on how much carbon has been captured, how much carbon they've helped capture, how much energy the project's generating and subsequently using, how much land's being used, and all of those statistics, as well as a weekly update that I'd publish. The byproducts from the device, as I mentioned before, will be sold, and all of the money will be reinvested into the project. Extra slides. So here's a much nicer version of the removing dissolved chlorine slide that I didn't want to add since it has a bit too much emphasis. Here's some development of the ideas. You can pause it at any point here to look over these closer. These were old versions of some slides. But anyway, thank you for watching!